Okay, very well. So let's get started. And um, can you see the screen, Dr. Hill?
Yes.
Okay, cool. So welcome to the non-experimental design webinar. The presenters today is Dr. Michelle Hill, Rosanna Topchian, and Armando Palladino. We all belong to the Center for Educational and Instructional Technology Research. Looks like Rosanna cannot hear me. Try to see if you can do something on the phone. I hope she's going to be ready to talk at least, right? So we're going to have, this is the outline. We're going to talk about the non-experimental design in a nutshell, causal comparative, correlational designs, and Rosanna is going to talk about beyond regression, and then we're going to have a questions and answer 15 minutes. So a brief introduction before I give it to Dr. Hill. So we, let me get this out of the way. This is a table that we created to, on a nutshell, just to make a quick comparison between experimental versus non-experimental designs. Important pieces of the experimental is the variables. You have an independent and a dependent variable, at least one independent. You have groups, an experimental group, a control group or placebo, and then you have an experiment location. And the purpose is to follow causation, right? Pretty much on experimental research. And you have the ability to manipulate the variables, aka the independent variables. You manipulate it as you wish, especially on experimentals. And then you have control experiments. You may have quasi-experimentals, not as rigorous as experimentals, and then field experiments. On the non-experimental, the topic of this webinar, we still have variables, independent and dependent variables. But if we have groups, the groups are used, and we use comparison groups rather than control group. You pretty much already have your groups. You have a natural setting for the research location, and the purpose is to compare situation, people, or phenomenon. And then you don't manipulate the variables. You use the variables as it is. Sometimes you can use ex post facto designs where the variables already happened and happened a year ago, 6 months ago, or you can just go ahead and study an environment as it is, but you don't manipulate the variables. And the typical courses type of design, surveys, case studies, correlationals, comparative, descriptive, longitudinal studies, and purpose. And the purpose is that specifically, you don't find causation. You cannot establish causation. There is no way. It's only a relationship. Okay, so I'm going to give it to Dr. Hill, and Dr. Hill, you tell me when I have to move the slides. It's all yours.
Okay, thank you. All right, we're going to start with causal comparative design. And I'll go over the objectives first. Next slide, please.
Hold on. There you go.
Okay, so we're going to look at the definitions, some characteristics, uses, the steps involved, statistics, and limitations. Next slide. Okay, just as a general overview, causal comparative research has non-experimental designs that investigate relationships. Researchers try to identify causes, although we're not looking at causes. They're looking at the differences that already exist within individuals or groups. These are suggested relationships because you do not have a complete control over the independent variable. You cannot prove or say it is a cause. Now, there are three types. You're exploring effects, you're exploring causes, you're exploring consequences. This means that you look at the relationship. For example, changes in X can cause changes in Y. Y can cause changes in X. Z can cause changes in both X and Y. Therefore, you cannot state that any one variable causes another. You must look closer and explain or explore those different relationships. Next slide, please. Okay, so some of the characteristics is an ex post facto type of research. That means after the fact, and it uses secondary data. Pre-existing differences or conditions, and some of these pre-existing conditions, hair color, things that you can't change, gender, another example, college major, political affiliation, disabilities. These are things that can't be changed. These are the type of pre-existing groups you might have. Now, there's a lack of control or the inability to manipulate independent variables, which makes it non-experimental. So you can make some reasonable inferences about causation. And reasonable is in bold because most times you cannot discuss causes. You can't say it's caused because it's random. An assignment is a requirement for a causal statement. Now, I'm going to give you an example. Over the weekend, this past weekend, there was a study on TV, and, well, not on TV, but TV. They started to discuss this study, and it was about vitamin D. And basically, it was saying that higher levels of vitamin D reduces breast cancer. So that really piqued my interest. So I'm paying attention now, and they start to go through all the different things that they did for the study. And so it was a randomized study. But what I want you to look at are the variables and the way they ended up talking about it. Okay, so at the end of the report on the news, the reporter stated that they didn't say vitamin D reduced the chance of breast cancer, but that it was an association. And so this is what we kind of look at with causal relationships. We're looking at the association. Although you may want to say it caused and it looks like it caused, there are so many other variables, you really can't say that that's a cause. And that's why I mentioned the reasonable inferences. It may be reasonable to say so, but there are just too many other things associated with it. Okay? You must be very clear when describing your results to make sure that you are discussing the associations and relationships and not causes. If there's a relationship between two groups, it is not an automatic cause. And sometimes with a chi-square is used to compare group frequencies to see if an event occurs more frequently in one group than another. Next slide, please. So some of the uses. When will we use a causal comparative research methodology? When variables cannot be manipulated, and some examples of the variables as mentioned before, gender, ethnicity, socioeconomic level, education level, religious preferences. These are some things that cannot be manipulated. And you would also use this model when experiments are not possible. If it's not possible because of location, or it costs too much, or it takes too much time, or when other methods will not work. It attempts to identify causes or consequences, while the assumption of this design is inaccurate and not always true. Next slide, please. Okay, the steps involved are just like any other research. Typically, you have the research question, you identify the independent and dependent variables, you select the participants, you collect the data, but the difference with collecting the data is you're looking at pre-existing data. and you're using things that have already occurred, and your groups are already put together. You're not manipulating the groups. You're not doing any type of experiment. You're using everything that has already happened. And then you analyze and interpret the data, and you report your findings. Next slide, please. So some things that you look at, you're comparing the averages. A lot of times you construct the frequency polygons to begin with. You use cross-break tables. You look at the means and standard deviations between the independent and dependent t-test. The t-test, the differences between means to determine whether the means of the two groups are statistically different from each other. You use the t-test for comparison of the two groups. The ANOVA for comparison of more than two groups. So your analysis of variance is used to determine if there is a significant difference in 3 or more groups. And the chi-square for comparison of group frequencies between groups. And then you can make inferences about these results. Next slide, please. Now, the limitations, as we talked about before, but just kind of to sum up what these limitations are, there must be a pre-existing independent variable, and you can't manipulate it. And those variables we talked about before, the gender, the age, there's a lack of randomization. Inappropriate interpretations can occur, making it hard to identify cause-effect relationships. Now, let's go back to the vitamin D study. There were mainly Caucasian women. The group did not initially have cancer, and all the women were age 55 or older. Okay, now that jumps down to that possibility of subject selection bias because they were all over 55. So even in looking at other studies, you can see how some of this is kind of related. There are often other variables that affect the dependent variable instead of the independent variable. And again, the independent variable cannot be manipulated. We never know if the groups were equal before the differences occurred. And then there are other threats like the location, instrumentation, and loss of subjects, and sometimes even the attitude of subjects we don't know. So those are some of the limitations of causal comparative studies. Okay, I'm finished.
Thank you so much, Dr. Hill. Very well appreciated. If you can please wait for the questions until we finish. And then
Okay.
I hope that Rosanna will be able to talk. I saw the microphone and it seems to
Can you hear me?
fine. There you go.
Good.
Hey, thank
Okay.
you so much. I can hear you well. Thank you.
Very good.
Okay, so it's always a glitch, right? It's always a technicality. Anyways, let's talk about correlational designs, two types, relational and predictive. When used, the types, characteristics, and assumptions. So when do we use the design? It's appropriate for exploring problems about relationship between constructs, construct dimensions, and item on a scale. For example, the age of a child may be related to the height, and the adult occupation may be related to his or her income. It's something also about causation here, and we're going to talk on the future slides, something that sometimes students tend to mistake. We have two types. Relational is just to identify the existence, strength, and direction of relationship between two variables. The synonym of correlation is association, and it is referred to the direction and magnitude of the relationship between two variables. The supporting analysis is correlation. Predictive is used to identify predictive relationships. This is something commonly used in business, in sales. You want to predict how much sales you're going to have based on different individual parameters, aka independent variables. So the design is used to identify predictive relationships between the predictors, and the outcomes criterion variables. Sometimes people use the word criterion, sometimes people use outcome, or you can use dependent variable as well. And the supported analysis is the regression analysis. We have different types, as we can see later. So when do we use these problems that beg for the identification of relationship or predictive relationship are appropriate for correlational design? Something that in the research methodology group and my colleagues in conversations I have with Rosanna and also with Dr. Hill now and Dr. Sloboda is about trying to elevate the rigor and quality of our dissertations. There's nothing wrong with doing correlational, not at all. But 90% of the proposals I see, I'm going to try to do a correlational design when there is more actually you can do, including linear regressions and go deeper, as you can see when Rosanna presents. So the theoretical framework for this type of design is supported by relational theories that attempt to test relationships between dimensions or characteristics of individuals, groups, or situations or events. These theories explain how phenomena or their parts are related to one another. The theory about relationship between the construct was first introduced by Carl Pearson, an English statistician, and then expanded by Charles Spearman, that developed a method to compute correlation for ranked data, aka non-parametric tests. And again, going back to what Dr. Hill was saying, correlation doesn't tell us anything about causation anyways, which is a mistake frequently made when interpreting the results of the analysis. Some other variables, time, relevance, whatever, explain the relationship. And in order to interpret the results of the analysis, we need to know the context. So correlation only tells us that a relationship exists, not whether it is a causal relationship. For example, individual salary level is associated with their test scores, and we find a correlation of 0.50, which tells us that people with higher salaries tend to score lower on the test. Does this mean that making more money makes you less smart? No, of course not. Or the classical example I use in class, the cost of pizza and the cost of using the subway, they have a high correlation. That means that the cost of pizza drive the cost of the subway? No, there are a bunch of other reasons why this correlation exists. So we use it, the linear regression, we want to predict. I told you the example in sales, in economy, they use this a lot. Based on parameters, you want to predict how much, how many chickens you're going to sell in February of 2021, based on the different parameters on independent variables. And regression is a step forward from correlation. That's what we're trying to do, if we can, with our students. Since with a good solid sample and design, we can predict outcome with the linear regression equation. We're going to see it in a minute. When the pure correlation would only show the strength of the correlations between two variables. That is measured from -1 all the way to +1. From a perfect negative relationship to a perfect positive relationship. And again, this should never be confused with cause and effect, since the two variables can be highly correlated without one causing the other. And it is worth to mention that on a solid and a strong regression, the correlation is implicit. That's why when my students come and say, I want to do a correlation, I always explore if linear regression is possible. We can have simple regressions, just one independent variable, multiple regressions with many independent variables, and logistic regression, when the outcome is dichotomous, is sick or is not sick, based on a bunch of independent variables, or yes or no. Let's look at an example. Imagine that I was interested in predicting physical and downloaded album sales. Album sales is the outcome from the amount of money I spend on advertising, and that's the predictor. We could summarize this relationship using a linear model by replacing the name of our variables into the equation. Next slide. Once we have estimated the values of the BS, we will be able to make a prediction. So let's look at this one. That's the equation. Y underscore I equal B0 plus B1 X1 plus the error. So let's see in the equation, Y subscript I is the predicted value, album sales in this case. B subscript 0 is the y-intercept, meaning when x is 0. B subscript 1 is the slope of the equation, and E subscript I is the standard error of the estimate, because we are never 100% sure. There is going to be always a margin of error. So we only need to plug the value of X, how much money we are spending on advertising, to predict album sales. And of course, this equation extends to multiple linear regression, and you're going to have multiple values of B. Again, in a linear regression, we never predict with 100% of accuracy. That's why the E error. We can do linear regression with interval variables, categorical variables, and a combination of both. And there is a very wonderful discussion that I always introduce in my statistical classes about the similarities between ANOVA and linear regression. And as you can see, one of the things you do in ANOVA, you're going to have categorical variables. And there are ways to do linear regression as well. So to be able to use categorical variables on multiple linear regression, we need to create n-1 dummy variables for the system to conduct a regression examining each variable with the other variables held constant. We're going to see an example in a second. For example, if we have 3 groups that we want to run a multiple linear regression, the below table shows the needed coding. There you go. We have this regression is regressing false memory, that's the dependent variable, against 3 groups of independent variables, represented by women either abused with post-traumatic stress disorder, PTSD, non-abused with PTSD, and non-abused without PTSD, 3 groups. But we only need 2 dummy variables. And you can see on, I think it's going to be better next slide when you see it right here. So when we code this into SSPS, we're going to have 1 column with the abuse PTS and 1 column with the non-PTS. So the result is that in the multiple regression, the first dummy variable will construct the abuse PTSD group with the non-abuse and the non-PTS group. And the second dummy variable will compare the abuse non-PTSD with the non-abuse group. This guy, Keith, 2015, included in the references, is a wonderful book I recommend that do a very, very good explanation on how to code these and different ways to do it. And finally, of course, we can also combine categoricals and continuous variables. Gender, for example, right? 0 and 1 plus, going back to my example, how much money I'm going to spend on advertising. So when using multiple linear regression, we can use 3 methods to enter the predictors into the analysis. Hierarchical method, you enter 1 at a time, and that will be based on past research and hypothesis. You can enter all the variables at once and or use the stepwise model, something that Phil doesn't recommend. And you can go ahead and check the book. Why are the reasons he doesn't like it? The assumptions on regressions is very, as you can, um, uh, gather that if you're going to try to predict with a linear regression equation, you must have a very good, statistical model. That's why linear regression is very demanding in terms of assumptions. So I'm going to go briefly on these 7 assumptions. Of course, you're going to have one dependent that is measured at the continuous level. You have one or more independent variables, right? That can be either continuous, categorical, or a combination, as I already show you. You should have independence of observations. Otherwise, you're going to have to do a different type of test, perhaps repeated ANOVAs. There need to be a linear relationship between the dependent variable and each of your independent variables, and B, the dependent variable and the independent variables. Your data needs to show homoscedasticity of residuals. That is, your residuals must show equal variances as you move along the line. Your data must not show multicollinearity. We're going to see an example, very clear example of what this is and why this is important. This happens when you have 2 variables that are highly correlated to each other. For example, age and experience, and we're going to see the example. And there, of course, should not be significant outliers. So this is one of the examples I use in class for the multicollinearity. We are trying to predict salary based on age, number of years as a model. These are women models, and attractiveness. So you can see that age is significant. And because it has 2 asterisks, it's because it's less than 0.001. And it's a positive relation between years and salary prediction. Age was also inversely related to the number of years as a model, indicating that the more years they work as a model, the less salary they would expect. This is not true, and this is related because multicollinearity. An explanation for this is found on the table below that shows the correlation between age and experience. It makes a lot of sense. This explains the reason why experience show negative values, because they both are reporting the same thing. You see that age and number of years a model are highly correlated. So the recommendation is that perhaps you should remove one of those. I would remove age, because somebody may be older than other, but this other person may have more years of experience. So that's why when you run the assumptions and you find multicollinearity and you find an example like this, get rid of one of the variables and rerun the linear regression. You have more than 20 types of regressions, but the most common use, linear regression, logistic, multiple multivariate regression. I was just recently talking to Dr. Lawrence about something we don't use, but it's possible to be done on SPSS. It's very similar to MANOVA, where you can enter on the GLM, general linear modeling, you can enter multiple dependent variables at once. We got polynomial regression, stepwise, and multiple regression. So with that said, I'm going to give it to Rosanna, and she's going to expand this going into the beyond regression discussion. Rosanna.
Hello. Can you hear me well?
Very well.
Good. Okay. So good evening. And as you see, there is life beyond regression analysis. And this beyond regression, there are more advanced types of analysis, which are very, very interesting. And in their core, I mean, in quantitative research, we think about models and we think through models. For instance, the average is nothing else but a model because we try to model the world. And our data that we collect, it is like the formula of the data is data equals model plus error. And the errors are all the individual scores that are different from the average. So next slide, please. So regression analysis allows us to look at, and we are going to, can you go to the next slide and then we will come back? No.
Oh, okay.
Go forward. Yeah. When you look at multiple regression, which is on the left-hand side, and the arrows. So the arrows show only direct relationship of predictors to the outcome, which is DV or dependent variable in the figure. But then there is a path model which allows you to also look at, if you look at red arrows. So for instance, there are several variables here, and I mean the variables are the same, but the way the relationship is analyzed, that is different. And the path model will provide us more information and more like a heavier story on the figure than the regression analysis figure on the left, because we will understand the direct effect of family background on achievement and indirect effect of family background through academic coursework, and then and then we can have the total effect of family background, which will go through all the arrows and everything else will be added up. So this is a very convenient, and those circles that you see, those are the error terms. In any measurement, as Armando mentioned, there are errors, and we have to measure them as well, because they also are included in any analysis that we conduct. Can we go back? So path analysis, actually in the core of path analysis is also the regression analysis. So regression is in the core of many different analysis at a higher level. And when is path analysis used? When we are interested in obtaining more detailed information about different effects in the model. So sample size in path analysis is similar to regression analysis. And the rule of thumb is that in regression analysis, we should have 30 samples plus 10 times predictors. So I think I had 5 predictors there. In this case, it will be 30 plus 50, and the G power calculates it 85. So I mean, not a big deal, plus minus 5. And G power is used to calculate sample size for different types of analysis, and we are satisfied with power of 80.80 and effect size of 15. So variable types should be interval ratio. We cannot use, I mean, we can use gender, for instance, because it's 1 and 0. But when we have, let's say, ethnicity, which is 1, 2, 3, 4, 5, I mean, you can definitely use that, but it would not make too much sense. So the specific characters of the path analysis is that it allows to identify direct, indirect, and total effects, and of independent variables on the dependent variables. So cause and effect in inferences are made based on theory, time precedence. What it means, there is a little judgment in it, researcher judgment. You need to make sure that the logic in the model is correct, because if you place, let's say, family background, that is the most initial thing that can happen to any person. So, and then after that, you have to sort of try to logically arrange the other variables, because if you don't do that, SPSS will analyze any data as you can see, family background is the initial variable, and it doesn't have this bubble, but all the other variables have because the arrows go towards them. So had I placed ability instead of family background, SPSS would have still analyzed the data, but my interpretation of the model would have been incorrect. So in other words, there is a story here because someone, okay. So there are three conditions for inferring causality. So there should be a relationship between the variables, because if there is no relationship between variables, it doesn't make sense to enter them into this model. And the presumed cause should have time precedence. In other, that was something that I already mentioned about the family background. And then the relationship between the variables should be true rather than spurious. In other words, it's not, sometimes students, for instance, a student came up with something and was trying to connect variables that logically did not connect. And they were thinking that it connects, but in reality, there was no logic in that connection. So that is something that needs to be, we need to make sure that the logic is also there. So there are, in quantitative research, we do slightly change some terminology. For instance, in non-experimental research, we use predictors, outcome, or criterion variable. In experimental research, we use independent-dependent variables. Now, in path analysis and all the analysis leading to structural equation modeling, we use exogenous variables, which are presumed causes. And family background was an exogenous variable and didn't have a bubble. And presumed effect, endogenous variables. Those are the ones that get to which arrows are directed. Definitely a path analysis has an advantage towards ANOVA because it tells more of a story than an ANOVA to the regression, because it tells more of a story than the regression does. Next slide, please. So here I'm showing path analysis results. So we use several indexes, and chi-square is one of them, to make sure that the data fits the model. And of course, I'm not going to talk about all of them, and you can read about them if you are interested. And there are certain, criteria that we need to meet. And then after that, we can say that, yes, so the model feeds the data well. And here I'm showing the different effects. If you look at academic coursework has pretty, the second large effect on achievement. And then ability has higher, what is larger effect on achievement because it's 0.551. And then, for instance, motivation, the direct effect of motivation is not that high. And family background also, it's a very small effect. Now, when you go to indirect effects and total effects, then things change. And it appears that, for instance, the indirect effect of family background is highest, but then it appears that the total effect of ability becomes highest when you look at the total effect because it's 0.682. It's very interesting to look at all these numbers and how they change. And then, of course, you need to be able to provide an explanation and interpretation of all those numbers coming from literature or from your own experience if you have one. Next slide, please. So assumptions of path analysis, all those structural equation modeling analysis have the same assumptions as the regression analysis, but then they have also additional assumptions, which, for instance, no reverse causation or recursive model. Now, when you look at the diagram on the right-hand side, shoe size and reading skill, and this is something that students always make a mistake, and they say this correlates with that, without understanding that correlation is a two-way thing. It's not one-way thing. And for instance, I mean, I can try to analyze and see if students' shoe size relates to or predicts the reading skill. But it's not about the shoe size. It's about something else that can be, which is age. So there is an intervening something that can be related to shoe size and reading skill. And but we cannot say that students who read well, the better the students read, the bigger their shoe size is, which means that this is not a very good relationship to think of or to try to explore, because it doesn't make sense. So in other words, it's very important to understand how those arrows can be drawn, because they cannot be drawn here and there and everywhere. So they need to have a logic. And again, if we make that mistake of drawing wrong, what are they, figures or diagrams, we are going to get the results anyway, but those results are not going to make sense. So as I said, terminology is slightly different when we talk about structural equation modeling, to which path analysis sort of is part of. Let's go forward. Next slide, please. Yes. Confirmatory factor analysis is usually used when we want to validate an instrument. It's an instrument validation technique, and it belongs to the family of structural equation modeling, and it also has a sample size requirement, which is an average of at least 10 samples per item on the instrument. For instance, if the instrument has 15 items or 15 questions, then if the student is going to use confirmatory factor analysis, then they should have at least 150 samples. So the variable types are again interval ratio, and the factor analysis also tries to allows you to identify whether the tested model fits the data well. Let's move on. Next slide. So this is how a factor analysis diagram might use, and this is a confirmatory factor analysis model with all the different indices that you can look at and select, and if the model doesn't fit that index, then you will have to decide to move, an item maybe, or to combine an item. And there is more to that, but I'm not going to address that. I'm just showing what it is. And this is actually the this is the construct or the general variable that has 3 subcategories, and on those 3 subcategories there are also some other subcategories, and under those subcategories there are also items. So in other words, this is this construct tree somehow that we test and we validate, and then when students say that, oh, I'm using a validated model, this is how the models are being validated. Next slide, please. Okay, so there is another type of factor analysis, which is called exploratory factor analysis. Actually, SPSS only does not allow you to perform confirmatory factor analysis, and you need different types of, you need either AMOS or STATA or R or some other things, M+. So exploratory factor analysis, it's possible to run it on SPSS, and this is from a student dissertation. The student claimed that they found an instrument, and then the instrument was used in an article, blah, 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 run the regression analysis and didn't find anything. I said, let's look at the construct structure. So this is the construct structure, and the yellow highlights are items that load on two different factors. When Armando said high collinearity, etc., that means that the same item explains this factor and the other, so contributes to two different factors. In other words, you would never know to which factor it really contributes. That's why it's safe to remove those highlighted items, which we did, and we cleaned actually the instrument, and then the student ran the analysis and got some results, because sometimes people claim that they validated the instrument and it's used only in one study, but when you do that, like when you use it with a different sample, the instrument falls apart. So you need always students need always to check the structure of the construct before they use it in an analysis. Next slide, please.
Hold on. There you go.
Yes. And this is actually, I'm showing a latent variable structural equation modeling. And latent variables are the constructs, general constructs. And this came from my dissertation, and I had several variables, etc. And I tried to identify the impact of team competencies, learning community, social presence, task type on knowledge sharing. And actually, this is a very interesting model to analyze, and it tells a story. And you can, what is interesting about structural equation modeling, here you have both the confirmatory factor analysis and the regression together. In other words, you can run one structural equation modeling without factor analysis, and then you can eliminate things and keep other things the way you want. You think that the model feeds the data, I mean, well. And of course, there is, again, much more to this, but I'm just trying to show you how we can think in quantitative research through models. And then for this exact model, next slide, please. You can again look at direct effects, indirect effects, and total effects. And then something else that I did, I looked at it using different subgroups, and I looked at males. In other words, I analyzed the model with males separate, females separate, white separate, black separate, age groups separately, undergraduate, etc., etc. And it appears that for like all of them, in all of them, I received the same significant results, which was an indication that the model probably is a predictive model of knowledge sharing in virtual learning teams, which was the topic of my inquiry. So next one, probably we don't have anything there. Yes, and here we put our references, and now we will take your questions. We have some 10 minutes, maybe 15 minutes, because we started some 6 minutes late. And we are ready to answer your questions.
Just want to add something before I give the floor up. Be sure that your microphone is on mute, or raise your hand, send me a chat, and I try to unmute, but you should be able to unmute it. Just want to say something about what Rosanna presented. We don't really have to be mathematicians, nor no deep calculus to do this analysis. The tools that we use at Phoenix allow us to run it. It's just a matter of learning how to interpret it, because if we really learn to do this, we can take our students to the next level. Because I see SEM as a real rich way to create dissertations from and look at the data from different angles. But that said,
that is very interesting. And something that, I mean, I learned from scratch, and I learned by myself, because what I was doing, my dissertation chair, he was a great person, and he said, I know this much, I can help you out, you know, I know ANOVA or whatever. And I said, don't worry, I'll figure it out. In other words, students sometimes need to take the initiative, because I mean, you can be the methods person or you may not be the methods person. In other universities, you don't always find people who are on your committee and who know, your exact analysis that you are doing. But I don't know how our students approach that, so. Any questions?
Well, oh, Derek, let me open the, you should be able, can you speak, Derek?
Yes, can you hear me?
Yes.
I can hear you well now, yes.
Okay.
Thank you for raising your hand.
One of the questions that I had is you mentioned that SPSS would not let you do the modeling, and
Right.
you suggested AMOS.
Yes.
Since AMOS is an add-on for SPSS, is that something that the university supports in terms of getting us access to, or is that something that we are on our own to get?
I think
So,
that's something that you will have to get on your own. I bought my perpetual license when I was a student, and but Armando knows a link where you can get $40 a year as a discount, like a student price or something, which is very good because I personally paid approximately $300 or $400 to buy the program.
yeah, I asked that question once.
Armando, you are too far. I cannot hear you.
University would say, but they say no. So, but that's what
Armando, your voice is not good.
This is okay. I think Paula wants to talk. Paula. Can you hear me well now, Rosanna?
Now it is better, yes.
Okay.
And Paula is muted.
It was some noise. Yes, I think I pay. I don't recall, but I don't think I pay more than $40 for a yearly license. And then you download it, and it automatically, it doesn't really work as an add-on into the SPSS as I used to, but you can use it interchangeable, right? You can use the SPSS.
You don't even need SPSS. You can use it with Excel as well. So if you have AMOS, you can use Excel with it. You don't need SPSS, or you can use SPSS if you have it.
You can read the SPSS output into AMOS. Next question.
You said Paula has a question, but you muted her.
Well, I did because I don't know if she unmuted her, so I'm going to unmute her again. Hold on. Paula?
Paula?
Paula? Paula? Yeah, I don't think so. Okay. Well, if no more questions, thank you so much. I am going to stop the recording. The recording is going to be available in the research methodology group in both places, in the webinars place and also in the calendar. We have a little bit of a problem now posting, but it should be fixed by Monday. So no later than Tuesday, Wednesday, you're going to have the link to download the presentation. And we also going to post the PowerPoint into the non-experimental link that Rosanna, Dr. Hill, and I manage. Thank you so much, and thank you for attending. I'm just going to stop the recording.
Bye-bye.
Bye-bye.